Imagine a computer so powerful it could design life-saving drugs in days instead of decades, create new materials from the atom up for perfectly efficient energy grids, or solve financial models so complex they are simply impossible today. This isn't science fiction. This is the world of quantum computing, and its most powerful engines, once confined to multi-million-dollar labs, are now becoming accessible to you, right now, through the cloud. Welcome to GE Fun Facts Online, where today we're exploring the dawn of remote superconducting processors. To understand this revolution, we first need to grasp why quantum computers are so different from the classical computers in our phones and laptops. A classical computer uses bits, which are like tiny light switches, either a 0 or a 1. Simple, reliable. A quantum computer, however, uses quantum bits, or qubits. And a qubit is far stranger. Thanks to a principle called superposition, a qubit can be a 0, a 1, or a blurry, probabilistic combination of both at the same time. Think of it like a spinning coin. While it's in the air, it's not heads or tails. It's a blend of both possibilities. Only when it lands, or when we measure it, does it resolve to a definite state. This ability to exist in multiple states at once allows a quantum computer to explore a vast number of potential solutions to a problem simultaneously. But that's not all. The true power-up comes from a phenomenon that Albert Einstein famously called spooky action at a distance. It's called entanglement. When two qubits become entangled, their fates are fundamentally linked. No matter how far apart you separate them, across a room or across the galaxy, measuring the state of one instantly influences the state of the other. It's this intricate, spooky connection that allows for complex calculations and correlations that are completely beyond the reach of classical machines. So how do you actually build one of these strange devices? One of the most promising technologies relies on superconductivity. Superconducting quantum processors are intricate circuits made from materials that, when cooled to extremely low temperatures, have zero electrical resistance. This perfect conductivity is crucial for protecting the delicate quantum states of the qubits. The heart of many of these circuits is a tiny component called a Josephson junction. It's essentially a tiny insulating barrier sandwiched between two superconductors. This setup creates an artificial atom with distinct energy levels that can represent the 0 and 1 states of our qubit. Scientists can then use precisely aimed microwave pulses to nudge these qubits into a state of superposition or entangle them with their neighbors, effectively programming the computer. However, building and operating these machines is a monumental engineering challenge. The very quantum effects that make them powerful also make them incredibly fragile. Their biggest enemy is a phenomenon called decoherence. Qubits are hypersensitive. The slightest vibration, a stray electromagnetic field, or a tiny change in temperature can cause them to lose their quantum properties and collapse into a boring classical state of 0 or 1. This decoherence, which can happen in mere microseconds, is the primary source of errors in quantum calculations. So how do scientists fight this constant battle? The first line of defense is extreme cold. To shield the qubits from disruptive thermal noise, they must be housed in sophisticated machines called dilution refrigerators. These are not your kitchen freezer. They are multi-stage cooling behemoths that use a mixture of helium isotopes to cool the processors down to about 10 millikelvin. That is colder than the vacuum of outer space. As processors get bigger with more qubits, the refrigerators have to scale up too. IBM's Project GoldenEye is a perfect example, a concept for a superfridge capable of housing the massive quantum computers of the future. But even in a deep freeze, errors still happen. The ultimate goal, therefore, is to achieve fault tolerance. The idea is to use quantum error correction, where the information of a single, perfect, logical qubit is encoded across many, less perfect, physical qubits. This redundancy allows the system to constantly check for and correct errors without disturbing the overall computation. We're not there yet, but researchers at Google have already shown that error rates can be reduced by increasing the number of qubits, proving the principle works. Both IBM and Google have public roadmaps aiming to build the first useful, fault-tolerant quantum computers by the end of this decade. Given these immense challenges and costs, you won't be buying a quantum computer at Best Buy anytime soon. So how does the world get access to this power? The answer is the cloud. Major tech companies like IBM, Google, Rigetti, and Microsoft have launched cloud platforms that provide remote access to their quantum processors. Using software development kits like IBM's Qiskit or Google's Cirq, which are based in the popular programming language Python, anyone can design a quantum algorithm, submit it to a real quantum computer, and get the results back. This democratization of access is fueling a global explosion in quantum research and development. Of course, if you're sending a sensitive computation to a remote server, security is a major concern. Researchers are already solving this with a technique called blind quantum computing. It allows a user to run a calculation on a remote quantum server without the server ever knowing what the algorithm or the data is. It's a bit like giving someone a locked box and instructions on how to manipulate the lock without ever telling them what's inside. This technique paves the way for secure cloud quantum computing in data-sensitive fields like finance and healthcare. This quantum future is being built by a global coalition of tech giants, nimble startups, and academic powerhouses. Industry titans like IBM and Google are in a race to scale up their superconducting processors. Microsoft is exploring a different path with theoretical topological qubits, while startups like Rigetti Computing are building their own hardware from the ground up. And they all stand on the shoulders of decades of research from universities like MIT, Stanford, and the University of Oxford, and government labs like the National Institute of Standards and Technology. Now for the most exciting part, what can we actually do with these machines? The applications are poised to transform entire industries. Take medicine, for example. The process of discovering a new drug involves understanding how complex molecules, like proteins, fold and interact. This is an incredibly difficult simulation problem for classical computers. But for a quantum computer, it's a natural fit. They can simulate molecular interactions with unprecedented accuracy, potentially allowing scientists to design highly effective new drugs for diseases like Alzheimer's or cancer, in a fraction of the time and cost. It's already starting. The pharmaceutical company Biogen is collaborating with quantum firms to accelerate their research. Or consider materials science. With quantum computers, we could design new materials atom by atom. Imagine creating a room temperature superconductor that could lead to a perfectly efficient energy grid, or a new catalyst that pulls carbon out of the atmosphere. By precisely simulating quantum behavior, we can engineer materials with properties we've only dreamed of. And then there's the world of finance. Finding the optimal investment portfolio is a classic problem with a mind-boggling number of variables. A quantum computer could explore all possible strategies simultaneously to identify the true optimal balance of risk and reward. It could also run hyper-realistic Monte Carlo simulations to analyze market risk with far greater speed and accuracy, giving financial institutions a powerful new tool for navigating economic uncertainty. So where does that leave us? Today, we are in what's called the Noisy Intermediate Scale Quantum, or NISQ era. The machines are real and powerful, but they're still limited in scale and susceptible to noise and errors. But the progress is breathtaking. Coherence times are extending into the millisecond range, a huge leap for superconducting technology. The roadmaps from the industry leaders point toward fault-tolerant machines within the next decade, computers that can finally solve commercially and scientifically valuable problems that are intractable for any classical supercomputer. The long-term vision is even grander, a global quantum network. This network would not only provide unhackable communication channels, but would also allow multiple quantum processors around the world to be linked together, creating a single, distributed quantum machine of immense power. The dawn of remote superconducting processors is more than just a technological milestone. It's an open invitation to researchers, developers, and innovators around the globe to start experimenting, learning, and building the future. We are standing on the precipice of a new era of discovery, one where the quantum leaps of today will become the world-changing realities of tomorrow.